Hello, everybody. This is Jen Pei from Simon Fraser University. It is great to meet you online. Thank you for coming to my talk about practicing the art of data science. In this talk, I will share with you some of the experience and lessons we learned from our data science research. Everyone talks about data science, but after all, what is data science? And we now know if we have to emphasize a subject carries a name of science, likely it may not be really science yet. The same applies to data science. Although we call it a data science, indeed is a combination of science and engineering. And of course, one important component is the art. In the rest of the talk today, you will see that in our experience, a lot of engineering and art components play important role in our data science practice. The whole process of data science is the whole pipeline from extracting data from all kinds of sources, clean data so that the data can be consumed by computers, and then we have the data pattern mining. We extract interesting and useful patterns from data, and using those data, we will build different kinds of models for different tasks. And then those tasks will be put into action, and we can extract understandable knowledge to present to human beings. And these several steps will form a loop, and human being is at the center of the loop. Through data science practice, we collect all kinds of general scientific principles and tools to build domain-oriented end-to-end solutions to extract interpretable knowledge. Many people ask me this question: what's the difference between data science and machine learning and artificial intelligence, which are very, very hot nowadays? To my understanding, they are related, but they are also different. One article from the Harvard Business Review said very well: the key skills for data scientists are not the abilities to build and use deep learning infrastructures. Instead, they are the abilities to learn on the fly and to communicate well in order to answer business questions, explaining complex results to non-technical stakeholders. Here, we can see data science, the focus is really on the communication between data science and human users. Let me use one example to illustrate this. Back to 2005, my group developed one approach to find frequent closed partial orders, which can summarize sequence data. Let's consider the following context. Suppose we collect the user behavior in a bank. Specifically, we look at in what order a user opens his or her bank account. For example, we see one customer to see, she opens a checking account, and then the money market account, and then the mortgage account, and then the registered education saving account. And we collect all the data. We want to ask what are the common things that those customers open their accounts. Our approach can find a frequent partial order among those actions, those steps. And the paper was published in ICDM 2005, got a little bit citation. Later on, the full version of the paper was published in the IEEE Transaction as a journal version, which have been reasonably well cited. And in order to make the paper, indeed, we have to come up with some applications, and we use some bioinformatics data sets, such as the protein-protein interaction data, to test our algorithms. We show some mini case studies, and well, the reviewers say, okay, the paper is accepted. But indeed, those case studies did not really involve domain experts deeply. Later, we had the luck to work with software engineer researchers. We apply approach to code analysis. We developed a tool set which is called mining and recommending API usage for software developers using these usage patterns. The paper was published in a conference and has been very, very well cited. As you can see, the same algorithm, but with the application background to software engineer, produces very, very different outcome. The impact is much larger if we can integrate with the domain applications. Our experience told us that the domain experts, the domain users, indeed, they do not care too much about the algorithm details. What they care is whether the algorithm can be adapted to their applications, and also whether the tool can be provided so that they can use the algorithm straightforwardly. So we can see from this example, there are several lessons I learned. The first is that the data science research should provide domain-oriented end-to-end solutions. It is much more than just coming up with another algorithms that can work on some kind of data. And here we have complementary roles for machine learning and AI. Machine learning produces very good models, but data science research helps people to obtain domain knowledge. The last is that in the data science development, a very, very critical point is the interpretability and the understandability. If we want to talk about interpretability and understandability, there are already tons of existing work on how to interpret, for example, a deep neural network. In principle, they can be grouped into three major ideas. The first idea is that we can look at every neuron in the deep neural network. We can try to visualize, reword map, or label those features that are learned by those hidden neurons. The weakness, the drawback of this approach is that quantitatively analyzing every neuron does not provide much actionable and quantitative interpretation about the whole neural network, about the whole model, because the whole model is not a simply linear combination or linear sum of all those individual neurons. The second major group of approach use those model mimicking methods. The idea here is that we can imitate the classification function of a large target model, and then we can build a transparent model that is easy to understand or easy to interpret. However, the drawback here is that because we reduce the model complexity of a mimic model, there's no guarantee that a deep model with a large VC dimension can be successfully mimicked by a simpler shallow model. The last approach uses those local interpretation methods. The idea is that we can compute and visualize the important features of an input instance by analyzing the predictions of its local patterns, local perturbations. However, one issue is that the perceptive distinguishable instances that are very close to each other may not be interpreted consistently in the same way. By observing the drawbacks of these three existing approaches, we look at where the challenge of interpreting and explaining deep models. Cecil Rudin published a paper last year talking about the challenges. Her position is very well set. She pointed out that explanations may not be faithful to the original deep model, and also interpretation often do not make sense or do not provide enough details to understand what the black box model is doing. The black box models are often not compatible with the situations where the information outside the database needs to be combined with a risk assessment. And black models with those interpretations can lead to an overly complicated decision pathway ripe for human error. Based on her observations, she clearly advocates that stop building the explanation of black box models. Instead, construct interpretable models directly. Inspired by the previous observations, we propose one idea here. We call it is exact and consistent interpretation. This is one of the major essential requirements we see that all those model interpretations should have. There are two keywords here. One is exact, one is consistent. We said we have two models, M and N. One model, M, is an exact interpretation of another model, N, if this M is mathematically equivalent to N. We use the mathematical equivalence to build a connection between this M and N. Because they are mathematically equivalent, those two models will behave exactly the same. For the second keyword, consistent, we require that a model M is a consistent interpretation of a model N if this M provides similar interpretations for classification on similar instances. In other words, if we have two instances, they are close enough, they should get a similar interpretation. They should not be interpreted in very different ways. The whole idea here is that we want to build a white box that behaves exactly the same as a black box as the interpretation. To build an exact and consistent interpretation of deep neural networks, we propose an idea on piecewise linear neural networks. Piecewise linear networks are those neural networks using activation functions that are piecewise linear functions. They are very popularly used. For example, the ReLU network, the MaxOut networks. The key ideas here is that a PLNN is mathematically equivalent to a set of local linear classifiers. So as long as we can get those local linear classifiers, we get an exact interpretation of the PLNN. Also, a local linear classifier covers the instances within a convex polytope in the input space. Therefore, the idea of an exact interpretation is to capture those convex polytopes. We build a tool is called OpenBox, which is an exact interpretation of a PLNN by an equivalent set of local linear classifiers in closed form, where each instance can be interpreted using the corresponding decision features. Let's look at how we can build an exact interpretation of a single instance. First of all, we define the activation status of a single neuron. As shown in the left figure, the activation status of a binary code. Each value of a status uniquely corresponds to one segment of the piecewise linear activation function. In the general case, as shown in the right figure, the hidden neuron adopts a piecewise linear activation function with k segments, and the activation status is simply a query code. Our method applies to the general case. So given a PLNN network and an instance, the activation status of all the hidden neurons are fixed. The configuration of a PLNN is then simply the cascade of the status of the hidden neurons. Next, let's see how to exactly interpret the classification result of an input instance X. For a fixed input instance X, the configuration is fixed. In this case, the classification function of the PLNN on X is equivalent to a linear classifier. The closed form of the linear classifier can be easily computed by a forward propagation, and the tuple of W and B just identify the decision boundary that exactly interprets the classification result of X. This is how we can compute the exact interpretation of a single input instance. In order to find the consistent interpretation, we only need to notify the following. Since the same configuration leads to the same linear classifier, an immediate question is what are the conditions of X and X pi, two instances have the same configuration. Let's denote by Zi, the input of the ith hidden neuron. By the definition of the activation status, we can derive the table in this figure, in the middle of the figure. Okay, and then apparently this column Zi represents the set of linear inequalities with respect to this X. We denote the set of inequality as P, and then give the following observation. We can conclude from on the right, we can conclude these three observations that interpreting the classification result of X by this classification function is exactly and consistent interpretation of X in all the convex polytope is CP. So in summary, our method interprets PLNN by two types of features. The first type of feature is the decision features identified by the matrix W of this classification function fx. These features interpret the classification result of the X. The second type of feature is the polytope boundary features. Those are the decision features of the polytope boundaries. These features capture the common features of all instances inside the same convex polytope and interpret why the PLNN uses this classification function fx as the classifier of X. Let me show you some of the experimental results to get a better understanding on what we are doing here. On the first figure A here is a training data set, synthetic data set. And on the figure B, we build a PLNN model which gives a pretty good classification result. Figure C shows the convex polytope in the same color, so that you can see how those convex polytope indeed distributed in the input space and interpret the classification result. And on the figure D, you can see that how those linear classifier of each of the polytopes that cover the decision boundary. As you can see, our model can construct exact and consistent um, interpretation of the original PLNN in Figure B. And also, these figures shows the comparison with the state-of-the-art method, such as line. As you can see, our method provides the exact interpretation, while line provide a pretty good interpretation, but is up and down, centered at the ground truth. Okay. And also in terms of the consistency, our approach provides a much better consistency results than line. Very recently, we further extend our approach to cloud AI services. One challenge in cloud AI service is that people put the models behind the cloud service APIs, and users cannot access the model parameters or training data. The key idea of our approach is that we can find the decision features for an instance to be interpreted by computing the closed form solutions to a set of overdetermined linear equation systems. And in order to obtain those equation systems, we use a small set of sampled instances. And we provide a very strong theoretical result, is that our approach can guarantee that the probability of exact decision features are identified is 1. The general idea is that if we independently and uniformly sample D instances from a hypercube that's covered by the same local linear model, then the matrix A is a full rank matrix with probability 1. And our OpenAI approach adaptively finds a proper hypercube containing a query instance. And for more details, please refer to our ICDE 2020 paper. Using the above two examples, I hope I convince you that data science is much more than just developing new algorithms. Indeed, interpretability is very, very critical. And also we need to consider the domain-oriented end-to-end solutions, which are highly valuable to domain experts. And knowledge learning with data science indeed is to turn black box models into white box models. Then the next question is, should data science develop more models or just assemble models to build powerful tools? And again, I want to use one of the examples to give you my answer. My group has done a lot of work on graph mining. Indeed, we have done graph mining for over 15 years. Why graph mining? Because graph is often used as a data model. And arguably, whenever you are facing a very sophisticated application scenario where the data are heterogeneous and very complicated, graph is almost the last resort of curse of the complexity in such applications. There are many different types of graphs, such as geographical graphs, relationship graphs, social networks, and so on. And if we think about graph a little bit, indeed, graph is a very ideal case of divide and conquer methodology in data modeling. Why? Because every individual node and every individual edge is very well constructed, while the global structures are weakly organized. This gives us a perfect tool to do a divide and conquer. There are many different works on mining graphs and networks because we can take multiple different views to graphs. We can look at the micro view, which contains the nodes and edge. We can take the macro view, which look at the global structures and the properties. We can also stay in between to look at the local structures and the behavior. Don't forget time. Time provides a huge challenge and opportunity for graph mining. And also there are many different important tasks. For example, finding patterns from graph, classification, prediction, clustering, outline analysis. Why graph computing is challenging? Remember, when we get efficient data processing, we are holding two key assumptions implicitly or explicitly. The first assumption is that we have well-structured data. The second assumption is that the data are synchronized. Unfortunately, in graph mining, neither of those two assumptions holds. Although graph has some basic structures like vertices and nodes, but there are many unstructured elements. And moreover, graph data can come in a highly asynchronized way. Edges can be added and deleted all the time, and nodes can be joining and leaving a graph all the time. My group have done a lot of work on graph mining, graph computing. We start from the lowest level, which is the graph construction, entity relationship identification, and then on top of that, we build graph databases, which can store and index graphs. And we also look at specialized graph applications to build specialized graph databases, such as the geographical networks and the social networks. On top of the graph databases, we conduct different kinds of applications, including the query answering, pattern mining, information flow, propagation, and inference analysis, privacy preservation, and machine learning. Let me use classification in graph as one example. Indeed, when we consider classification of graphs, we can have many possible options. What to classify? Do you want to classify nodes or do you want to classify edges? And indeed, one of the ongoing exciting work I'm doing is to classify subgraph structures. And then, what information to use? Do you want to use attribute information, views on graphs, the neighborhood patterns, and also don't forget time. You may consider classifications on dynamic networks. We publish some of the papers in the good places on different kinds of graph application tasks. One question came out after a while is that why our papers are not well cited. Let's look at another graph mining task, clustering. Clustering is an even more interesting and more subjective and more dynamic area for graph mining. There are many different ways to define clusters, and there are more information can be used, such as the rich information, such as the rich information in those nodes and edges. And also, once we look at the dynamic communities, there are many, many more choices. In the last several years, we did a lot of graph clustering. For example, one paper we did in KDD 2016 is about the, we call gangs in war. The idea is that we try to find the clusters, like here. Within the cluster, the nodes are highly consistent. They have the similar opinion. Their communications are more about the same subject, same topic. However, among different clusters, they hold very different opinions. Their communications are more like a fighting against each other. And recently, we also look at the density bursting subgraph. The idea here is that we look at the temporal graph and see how the transportation may emerge or may rapidly change over time. Our papers have been published in quite good places, like VLDB, KDB, ICDE, but again, if you look at the citation numbers, they are not very high. We think about these seriously. We find there are several important things. The first is that the classification and clustering work I just talked about, we just try to solve one specific problem at a time and develop one specialized solution. When we do that, from the academic point and from the industry point, they are not satisfactory. The reason is that from the academic wise, what are the general principles and methodologies? From the industry wise, what are the general and adaptive solutions for many problems of the same similar kind? We do not give the general solution so that the industry users have a challenge to turn those problems into their specific scenario. And we realize data science should connect problems in vertical domains and the general solutions. So instead of working on specific solutions, one idea is that we need to look at the off-the-shelf solution scalable in deployment. And we also should give people tools to encapsulate problems so that they can transform into customizable units. Let me use one example to illustrate what I'm talking here. Recently, I work in network embedding. Network embedding essentially is that we try to transform networks into vector data so that we can use general machine learning methods on graphs. We turn these graphs into the vector space. Of course, when you do the transformation, you may lose some information. So you need to preserve something in your embedding, in your transformation. Then we have different things that can possibly preserve. For example, the transitivity and symmetric transitivity, the communication, the complexities, and the higher order proximity. Those are just some possible options. And also, learning these transformation is a lot of work, particularly for practitioners. So we need to give a general automatic framework similar to AutoML, which can help to build a hyperparameter optimization framework. To further understand what the network embedding means, consider these graphs. We try to map a graph from the graph representation to the vector space representation so that the nodes belonging to the same cluster will be mapped into the positions in the vector space that are close to each other. And if we can build such a connection, such a embedding, then one advantage is that we can think the graph is embedded into the vector space. At the same time, we can use the vector space representation to regenerate graphs with similar distribution. We conducted several approach in this network embedding. For example, in our early study, we look at the asymmetric transitivity preserving embedding. The idea here is that in the directed graph, and we have two nodes, and a node may serve as a source and target of different edges, and they have different roles. Instead of mapping one node into one point in the vector space, what we can do is that we map one node into two different vectors in the vector space. So the details can be seen in our KDD 2016 paper, and I will skip the details here. As another example, there are two types of network structures: the microscopic structure, which focuses on the pairwise relationship or similarity between nodes, and the mesoscopic structure, which contains a higher order structure that is sort of like the commodity structures. So we can construct the modularized non-negative metric factorization model for commodity preserving embedding so that it can preserve the commodity structures. And we realize and admit that the constructing network embedding itself is very time consuming. So in order to help the users to quickly come up with good embeddings, we propose a model similar to the AutoML methodology that can construct the configuration of a network embedding automatically. So this is the general idea of our Autoany model. There are two steps here. The first step is that we sample several small subnetworks from the original large-scale network using the multi-star random walk here. One question is why we use random walk here instead of simply just sample a graph. The tricky thing is that if you only sample a subset of nodes as in a network, those nodes may not even be connected. It does not really represent the network structures for the network embedding task. Therefore, we have to use the multi-star random walks here. In the second step, the signature extraction module produces a signature for each network, including both the subnetworks and the original network, to facilitate the measurement of similarity between two networks. The signature is based on the Laplacian spectrum, which captures the network properties comprehensively and is capable of differentiating between the heterogeneous components. And the last step, we developed the meta-learning module. It trains a Gaussian process meta-learner on the sample subnetworks to distill transferable meta-knowledge about the optimal hyperparameter configurations. Our paper was published not too many years ago, and network embedding becomes a very hot direction now. And as you can see, the number of citations to our papers, including both the specific network embedding methods and also our survey on network embedding, are very, very high. And those numbers are indeed was the number in last November. I'm sure the number nowadays will be even much higher than these. There are a series ongoing work on network embedding in my group, and they produce very interesting and useful result tools for practitioners. Through the several examples I just talked about, I hope I can make it clear that data science indeed is a connector, that connecting general solutions and vertical application problems. Data science frameworks, methodology, and platforms really can help to build an interface among data, science, and applications. To reiterate, data science procedure involves extracting data from different sources, data cleaning, mining patterns from data, and constructing models. More importantly, we need to extract interpretable knowledge, and then we connect the general scientific principles and tools to domain-oriented end-to-end solutions to interpretable knowledge. Data science is just as beginning. There are a lot of work to be done in the future. For example, data strategies are important for enterprises and organizations. Every company is talking about the digitalization and the data science strategy. However, in order to fully implement the data strategy, there are a lot of things need to be done. For example, here, when we say data as asset and resource, we need the data pricing strategy and tools. And when we talk about data privacy protection, we need the privacy assessment approach and enforcement approach for regulations like the GDPR. And data is for collaboration, and how to build business products driven by data collaboration remains a big challenge for many industries. And of course, we need to do the organization optimization in order to make sure data is really a strategy. Let me use data privacy as one example. Back to 2008, Backstrom, Dock, and Klimper published a World Wide Web Best Paper Award winning paper on data privacy. Essentially, they claim that, well, even just say anonymization of social networks is not sufficient to protect the privacy in social network. Inspired by their question and challenge, we developed a very simple yet effective framework for social network anonymization. The idea is that we can process the vertices in the degree descending order, and then we can greedily pick a k anonymized vertices with the largest degrees and the most similar one neighborhood to form a group. And then we can anonymize the vertices in the group so that they have the isomorphic one neighborhood graphs. And we iterate this until the graph is k-anonymous. The rationale behind our approach is that the vertex degrees follow the power law distribution in practice, and those vertices of large degrees are the victims of neighborhood attacks. And the small world phenomena, in fact, helps us. We can add a small number of fake edges. Those fake edges may not affect the network connectivity dramatically. And also, our approach has a very simple and straightforward convergence in mathematics. If you keep adding edge, at the end, after all, you'll form a complete graph, which is naturally k-anonymous. Our paper got the 10 years Best Paper Award in 2018. However, if we ask the question, was the privacy problem solved? Unfortunately, no. Although there are privacy models one after another, but there's still privacy leakage and abusing instances again and again. There are very few models published in academia have been put into practical use. The main obstacle here is that the strict assumptions about the attacker's background knowledge and the data utility really hindered the real applications of those privacy models in specific scenarios. If we ask, what is privacy after all? The one annotation is that privacy is really the right to be forgotten. Should be being free from being observed or disturbed by other people. And the natural privacy intrusion is that some people, particularly or those unauthorized people, post transaction data retention. And also, there are inappropriate second use of data, which are one kind of privacy intrusion. So the challenge here is that we need to build persistent big data applications, and we need to have the offline and continuous AI model training, and we use some blockchain technology to record this procedure. And I believe there's still a very long way to go because data usage authorization and privacy auditing based on business scenarios is something we need to do. And also we need to eliminate undefined or not well-informed data usage. And we need to build interdisciplinary solutions to privacy preservation. So thank you for your attention. And I hope the talk I just gave can give you some useful information. Stay well and stay safe. Thank you.